now move into the most common model of bonding that we see in organic chemistry. It's valence bond theory and hybridization. Now, it's the most common method in organic chemistry because it provides us the most information while also being the sort of easiest tool to use. So it sort of meets that sweet spot where it's simple enough to understand, but is also an accurate depiction. Now, valence bond theory and hybridization is a mathematical model. In other words, this is not a real thing. It's a mathematical thought experiment that allows us to explain bonding. It also allows us to explain molecular geometry and lone pairs around a central atom, while also considering the orbitals present. Now, you would have learned about orbitals in your general chemistry courses. Let's start by thinking about a simple organic molecule, methane, CH4. Now, we know methane exists. We know CH4 exists. But if I asked you to say, write me out the electron configuration for carbon, you would write 1s2, 2s2, 2p2, where the division between the valence and the core is right here. So we see that we have 4 valence electrons. And that makes sense. We want to make 4 bonds. But if we think deeply about this, we say, but wait a minute. We have 4 valence electrons and we want to make 4 bonds, but only 2 of these electrons are unpaired. So how can it be possible to make 4 bonds? Well, only having 2 unpaired electrons. And this is where hybridization will come in. So we know carbon makes 4 bonds to 4 hydrogen atoms, but when we consider these orbitals, there's a problem. There's only 2 unpaired electrons, as we saw on the previous page. 2 down here and 2 up here in 2 of the p orbitals. I picked the x and y arbitrarily. So in order to explain how we could possibly make 4 bonds, we consider this thought experiment where we take an electron from down here in the low energy orbitals and we promote it up to a high energy orbital here. You'll notice that I don't flip the spin. That doesn't really factor into our consideration, but I do want to draw your attention to it. And now what we do is we say, okay, we've excited an electron. We now have 4 unpaired electrons. This is good. But we need to hybridize these orbitals to form every sigma bond. And so we hybridize all the orbitals that have electrons in them. In this case, that's the s and all of the p orbitals. When we think about hybridization, we think about the additive p and s orbital. Now you'll notice the top half of this has constructive interference. So I get a big lobe, and the bottom half has a little lobe like this. And so we get this hybrid orbital like so. My drawing is a little bit less nice than this nice one I've provided you here. We call this an sp hybrid orbital. And we consider the fact that we make 4 hybrid orbitals because we needed to use all of the orbitals present. This will be important to us in just a moment. Let's start by looking at these new orbitals. So you'll notice now, instead of having an s and 3 p orbitals, instead we have 4 sp3 orbitals. And importantly, 4 unpaired electrons. Now we can make 4 bonds to the hydrogen atoms around the carbon. So when we come back to methane, when we come back to CH4, this carbon here is called sp3 hybridized. And in fact, any atom that has 4 sigma bonds like so will be sp3 hybridized. These have bond angles of 109.5 and it's under the family of the tetrahedral atoms. And this will be important to us. we now want to start to think about what happens if we are to make a pi bond and how that affects the shape. So let's take a look. So now we have a carbon here with a pi bond, considering ethene. In this case, each carbon atom makes 3 sigma bonds and 1 pi bond. Now, a really important mantra to remember in organic chemistry is pi bonds require p orbitals. So they cannot be hybridized because they need to stay by themselves in order to make that pi bond. We apply the same thought experiment though. We take an electron, we promote it up, we leave 1 p orbital alone. That's going to be important because that needs to go make the pi bond. And then we're going to take everybody else here and hybridize them. You'll notice a new name, sp2. And that's because we have 1 s and 2 p orbitals to consider. Pi bonds require unhybridized p orbitals. Sigma bonds and lone pairs require the hybrid. So hopefully you're starting to see a bit of a pattern. Now, it's important to also keep in mind that we're going to have a relationship with bond strength, length, and the single, double, and triple bond. For bond strength, triple bonds are stronger than double, which are stronger than single. And for bond length, the triples are the shortest and the singles are the longest. Bond length and bond strength are inversely proportional. So here is your introduction to hybridization, something you would have seen earlier in your chemistry life, but a good reminder of an important concept as we start to move into more complex examples.